now I cannot move around. That's but okay, that's fine. No, I'm okay. It's fine. Yeah, I put that in my interact. Let's see if it works fine. Yeah. Okay, good. Well, good morning, and it's a real pleasure to be here. What I wanted to do today is give you a little bit of perspective. You know, in the last couple of years, I've been heavily involved in the design of products that cater to AI requirements, especially in the embedded as well as the cloud space. And I just would like to give you some insight on that, and also some of the challenges that we face, and hopefully, you know, how some of the technologies that you are all looking into can help in overcoming this, and so we can provide you then with, you know, better hardware that can help us then, you know, design better algorithms that can help us to design better hardware, right? So, talking about, you know, supporting each other. So, okay, I always start with this slide because, you know, these days there is so much going on about AI, and I really want to make sure that everyone understands the opportunities that AI is bringing to the world. I think AI is going to be so impactful for us that I definitely think, you know, as some people already said, we can compare it to the emergence of the internet, and I strongly believe that. And so what that means is it will be a dominating factor to define, you know, how our software will look like, how our hardware will look like, and it's driving a lot of you know, the requirements that we are getting today in AMD for our products, be it in the embedded space as well as in the cloud space. And now one of these things is, so there's a lot of good news, a lot of potential for AI, but clearly one of the observations is that there is coming towards us an insatiable demand for more compute. And I remember when a couple of years ago AMD announced you know, the exascale computer, the Frontier in El Capitan. You know, a lot of people were saying, well, you know, why would you need that much amount of compute power, perhaps for some exotic applications that the national labs need and so on. But it's clear now that you know, it's not anymore the national labs that are driving you know, the forefront of compute. It's now the requirements that we get from the hyperscalers, the Microsofts and the Googles and the Metas and the likes, in terms of servicing, you know, AI. And you probably all read in the press about, you know, the shortage of you know, devices and how hard it is to kind of build out infrastructure to keep up with the growing demand of compute. So that's one of the challenges that we are facing, is you know, meeting that kind of demand. But together with that, we are also challenged with the underlying technology that helps us in delivering that compute demand. One of the things is, you all heard the stories, Moore's law is slowing down and so on. And some of it is true, but the reality is we can still continue to increase the density of the transistors. But what is actually really slowing us down is the energy efficiency of the systems that we are building. I think what's limiting us today with today's technology in terms of you know, unleashing the full potential of the capabilities of the amount of transistors we have available to get into the devices and create the compute nodes that are enabled by these devices, is the energy consumption. It's really a major issue, and you know, the efficiency of the, you know, the energy efficiency of the you know, compute nodes that we are building is kind of lagging the capability actually that we potentially could deliver, you know, in terms of performance, because of you know, the challenges that we see there with energy consumption. So that's a really driving factor for us. And then another aspect that we see is that when we look at AI algorithms, they are kind of going in an interesting, challenging direction. So when you look at, for example, the roofline model of a specific compute architecture, so the red line gives you kind of the boundaries of the compute, the performance capabilities of a given architecture. And so what you see there is the dashed line, and on the left of the dashed line, algorithms that fall into that category, in that area on the left line, are typically algorithms that are bound by I/O and memory bandwidth, not so much by compute requirements. So the performance of the architecture for executing these algorithms is limited by the data movement between the memory and the basic compute component in the system. On the right of the line, you see the algorithms that are more bound by what is the compute density that you can bring into one compute node. So how many LUs and so on can you crank into one compute node? So now what you see two trends actually. You see, first of all, if you look at the algorithms, you see that the new algorithms that we see in the world of AI, and specifically when we talk about deployment of AI and inference and so on, you see that these algorithms are moving to the left. So that means that in terms of the operations per byte that you take from the memory, you see that you have less and less arithmetic operations that are executed on a piece of data that you get from the memory. So that means that there's much more traffic going back and forth to the memory than there is actually reuse of data into your compute component. And so what you see is that more and more algorithms are moving to the left. And then when you look at the trend of the technology and the architectures that are enabled by the technology, what you see is that the dotted line, vertical dotted line, is moving to the right. So you have two things that work against each other. You see, first of all, relatively speaking, the I/O becomes more and more a drag to the capabilities of your hardware component. In other words, the memory transfers and the data movement is limited by the technology capabilities, and it's evolving slower than the increase that technology can give you in terms of compute capabilities. So you see that dotted line move to the right from a technology perspective. So these are two trends that are cumbersome and challenging, to build products that cater, to the requirements of AI algorithms. So I think one of the important aspects here now is then, in order to cater to that insatiable demand that comes from AI, clearly there has to be a more holistic thinking about design, and we have to look at all knobs that we can turn, in order to build solutions that can cater to the compute demand within the bounding box of the energy, that's allowed to be consumed by these compute applications. So that's one of the important messages here, and we have, of course, several tools at our disposal for that, and the number one thing is of course is 3D stacking, and we are just actually at the beginning of that, but it's definitely one of the levers that we have in terms of dealing with some of the challenges that we see for AI computing. The other aspect is what I would refer to as domain-specific architectures and also software flows that allow you to kind of still have programmable architectures, but that take into account much more specific the requirements as they come from the AI world. AI algorithms have very unique characteristics that do not necessarily require, you know, the broad capabilities that we have been used to, that we see in the CPU world. And then another aspect is we should not only look at, you know, when we solve a problem related to AI, to just, for example, the cloud, and assume that we have this massive infrastructure that will help us. We will have to start thinking at the system level and think about, when we have an AI problem, how do we, you know, partition that problem between the cloud, which is of course a very important infrastructure that needs to be there, but also between the edge, where we potentially have you know, millions of client devices that could work together to solve some of the problems. And then the final thing is that we have to realize that it's not just about compute, right? When we talk about AI, we all know a lot of it has to deal with massive amount of data, be able to deal with that large amount of data, and how can we efficiently store, structure, access, move data in our architectures. So the first thing is 3D, and I'm sure you have heard a lot about 3D. I mean, several years ago, people started introducing what now is understood as 2.5D, where we have a silicon interposer, you know, that allows us to connect different dies in a package with a higher density of wires than you would traditionally see between packages, or even in an MCM. And to a certain extent, that was the first step in dealing with some of these challenges that I was referring to, like I/O bottlenecks and so on, and that gave rise to things like also HBM and the likes, was enabled by that technology. And it definitely kind of you know, delayed the pain a little bit that you know, we see in terms of you know, the challenges for data movement in AI applications. But there is a fundamental challenge, you know, with kind of a 2.5D type of architecture. That is that, whereas to increase your compute capability, you have two dimensions that you can use. You have the X and the Y dimension, where you can scale and you can cram more, you know, compute functions into one die, and as technology scales, you can continue to do that. But then at a certain moment, when you have to go off the die, you can only scale the density of your interconnect in one dimension. You have the beachhead of your die, which is basically a one-dimensional thing, and so you have only one dimension that you can play with, you know, to scale your I/O, whereas you have two dimensions to scale your compute. And you can see that you know, you're only increasing the gap, I would say, between a balanced I/O capability and a balanced compute capability, and that's where true 3D comes in, where you really are trying to integrate active on active dies, and where you can build in the end true three-dimensional architectures, where you can scale now the interconnect between your different functions in an extra dimension. You know, you can now scale your interconnect, if you have 3D, also basically in 2 dimensions. So, and some of that is of course, is becoming a reality, right? So, 2.5D originally came along quite a while ago in AMD. We used it basically originally to deal with some of the yield problems. It was like, how do we build a bigger FPGA out of smaller FPGAs and still have a really big FPGA, but don't give up on the high connectivity density that an FPGA requires. And so that's how you know, FPGAs were the first actually to embrace 2.5D. Then, you know, the memory guys started leveraging in to build HBM. And then what happened was we also started to see you know, how we could now combine different technologies with each other. And you see there in 2019 we had our first heterogeneous product, which was our EPIC CPU processor, where what you see in that picture, you see 4 compute dies and you see 1 I/O die. The big die in the middle is the I/O die, has all the infrastructure for memory controllers, PCI Express, I mean all the I/O capabilities. And typically, you know, that die is in a little bit of a lagging technology, whereas the compute dies are in the most advanced technology. And then, you know, for the first time last year, we announced the first product with active on active, where we had literally added an extra layer of cache to our CPUs by adding a vertically stacked static memory on top of our CPU, and that was basically the first time that you know, we really introduced active on active, which was, you know, mainly dealing with some of the practical problems that you had in terms of thermal and mechanics and things like that. It didn't really leverage too much the opportunity of you know, very high bandwidth, because, you know, it was not required in this specific case. But then, you know, this year we announced the MI300, which is our latest data center GPU product, and that basically combines a little bit of all the technologies now. If you look at that, the MI300 has about 13 chiplets. If you don't include the 8BM, on top of that it has 8 HBM stacks sitting in one package. So it's a pretty you know, complex device, and it combines 3D technology. It has accelerator dies. So basically you have first active interposer dies. There are 4 active interposer dies, which you can compare them as all the dies that are providing the basic infrastructure and I/O for your chip. And then on top of that, we stacked accelerator dies, which could be, for example, GPU dies, GPU compute dies, and we combine that with 3 CPU dies, which basically each CPU die has 8 CPU cores on there. So, and we can mix and match, right? We can have, for example, what we call an MI300X product, which has nothing else but the GPU dies on top of the interposer dies. We can have, you know, dedicated accelerators, more specialized accelerators in there, and so we can really mix and match, and we combine basically 3D active on active. The accelerator dies and the CPU dies are sitting on top of the interposer die. The interposer die, the active interposer die, the active interposer dies are connected to 2.5D technology. So you have the whole mix of technologies combined in one system. So this is the current status. Now, moving forward, you know, clearly we expect that there is going to be more and more leverage, you know, from 3D, and we anticipate that, whereas today, you know, the kind of the chiplets we are talking about and that we're stacking in a 3D fashion are, you know, kind of systems that stands on their own. We anticipate that more and more the granularity of the functions that you will you know, stack on top of each other will get smaller and smaller as you are improving, you know, the pitch that you can have from your interconnect between the different dies, and also as you are capable of dealing with some of the thermal challenges that are coming with stacking active and active. I think at some of the research organizations, people are today even thinking about starting to use die stacking to kind of stack transistors on top of each other, really create 3D structures where you stack transistors on top of it. So that's the kind of the granularity that people are today thinking of. So, I mean, organizations like AMIC, for example, are already looking in this kind of capability. So you see clearly there is going to be a trend where, you know, a lot of the 3D stacking today, you still recognize your traditional architectural thinking in there, but as you move forward, you literally are going to think about really a 3D space where, you know, you have fine granularity of functions that are kind of placed and routed over a 3D kind of implementation. So that's the direction where we go from a 3D perspective. The other important direction that we see on the silicon side is about domain-specific architectures. So you know, we all know, of course, that a CPU is a very solid workhorse of the industry, has been doing a lot of things, can be, you know, used in a very broad spectrum. But then, you know, we have the GPUs that are kind of a little bit more narrow, massive multi-threaded. You're not going to necessarily throw all the problems that you throw at the CPU at the GPU. It's for a more narrow application domain, it's more efficient. And then you have specialized accelerators which starting to emerge. As AI is becoming so important, you see more and more activities going on there in building even more specialized accelerators, which are still programmable. This is a somewhat older chart, but it gives you a little bit of you know, the kind of value proposition you get by domain-specific architectures, and it is applied on some of the architectures that we today in AMD are developing. You have our traditional CPU, you have our you know, graphics GPU, then you have our data center GPU, and then you have our specialized AI accelerator, which we refer to as AI engine. And you see the kind of compute efficiency that you get, you know, for a specific workload, specifically, of course, in this case, when we talk about AI defined workloads. So you can gain so much more out of specializing your architecture towards your domain that you can never achieve that by, you know, going to the next manufacturing capabilities and so on. And so that's the second pillar, I think, that will allow us to cater to, you know, the kind of requirements that that all of you have. And when I talk about domain specificity, what do I mean by that? And I will say a little bit more there about what we are doing on the AI engine side of things. So first of all, and you know that probably better than I, the arithmetic in AI is definitely it's not the same requirements than when you're dealing with a big scientific simulation environment or something like that. So people are starting to look at all different kind of data types, and you will see, you know, a lot of news coming there, I think, from the industry, where people are playing around with different exponents, different mantises, try to reduce the data type, because one of the things you see is that you know, a lot of these AI algorithms are very tolerant to reducing the accuracy of the data and the data types that you're using. Now think about it, if you can handle a computation in 8-bit rather than 16-bit, well, that means that you can reduce your storage with half of it, you can double the bandwidth of your memory, you can cramp 2 times as much compute power in one square millimeter. So there's all these benefits you can get, and so there's a lot going on now in the world of AI about, you know, what are the best data types for what type of algorithms, and even in the AI world, right? I mean, large language models, for example, are much more tolerant to smaller data types, whereas you know, CNNs are for example, a little bit less tolerant, and so you will have to pick data types dependent on the class of AI algorithms that you're working with, and your architecture has to be able to accommodate that and then allow you to take benefit of that. So that, think about the message I gave, you know, you have I/O bottlenecks, you have memory bottlenecks, so really picking the right data type is an important aspect, I think, of your architectures. Another important aspect of AI is that it's very data flow oriented. It comes with a lot of sparsity. So when you look at a lot of these algorithms, you know, what you see is that if you look at this data dependency graph, or the data flow graph, I should say, a lot of the edges between the nodes, a lot of the weights are close to zero. You know, a lot of the activations are zero, and so you do not want to waste energy in terms of you know, storing less relevant data, doing computation, and allocating resources to computation that is you know, not necessarily, and so on. And that means that you have to come up with an architecture where your compute efficiency is taking benefit of these characteristics of AI algorithms. For example, you know, you still see a lot in the press, people talk about, you know, the performance of some of the AI accelerators, and they talk about things like peak performance and so on. I think in AI that doesn't mean squat, it doesn't mean anything, because many of these applications, traditional hardware architecture has like 10% efficiency. It means that overall you're actually effectively using 10% of your compute capability that you have. So you have to think about architectures that can cater more to the characteristics of your AI application, and make sure that you can boost that efficiency of your compute resources, you know, from 10% to 90% or something like that. And so that's where you know, data flow architectures come into the game. Another aspect is, of course, when you talk about cloud to edge, when you deal with the edge, you have new requirements, things like, for example, determinism or latency, and you have to make sure that you know, when you leverage AI algorithms in these applications, that you cater to these requirements. A traditional architecture, for example, has a lot of shared resources. I mean, caches, for example, is a good example of that. Now, that can create sometimes issues in the context of determinism, right? When you start a PowerPoint and you have to wait in one moment for a few seconds, and the other time you use PowerPoint, it gives you an instant response or so, you don't care too much about it. But if you hit the brake of your car, you want to make sure that it every time is exactly what it's supposed to do, exactly the same. So there has to be determinism, and of course low latency too, as I would say. So there are some requirements when you start thinking about deploying AI on the edge that impose certain you know, capabilities that the hardware has to cater to, which are not typically seen, I would say, in traditional compute applications. And I already talked about some of the data types, right? And so a few words there about what in AMD we have been doing on that, and as I said, I showed you that bar chart where I showed you the difference between CPU, GPU, and then AI accelerators. So this is basically what I'm talking here about is one of these AI accelerators, which is an architecture that, first of all, it's a data flow architecture. What does that mean? Data flow means that it's basically the data that is triggering the compute, right? It's not like the compute that is you know, kind of asking for the data and potentially stalls when the data is not there. You know, in a data flow architecture, the data moves around towards the compute, and when the data arrives, it triggers the compute in a very simplistic way. And it's very similar to a GPU. It has a massive amount of compute engines. In the case of the AI engine architecture in AMD, we have up to 400 of these superscalar VLIW architectures. Each AI core is a superscalar compute engine, and all of them have local memory. And so what's one important aspect, remember that you know, when you deal with AI, a lot of the efficiency is determined not just by the compute, but also how efficient your compute is, and how efficient you bring the data, make the data available to the compute, right? So, and one of the benefits of a data flow architecture is that you can literally customize your data movement towards your application at hand. I mean, you could pipeline, for example, your data movement, which I could imagine, like when you think about a video pipeline or something like that, your parallelism is created by pipelining, you know. But when you have a more traditional machine learning algorithm, you might want to broadcast your data to your different engines. So you can, in a data flow architecture, you can literally program this data movement, and on top of that, you kind of pipeline your compute and your data movement. You never will have compute that stalls, you know, because it's waiting for data. It's like both the data is moving around, and at the same time you're doing in a pipeline fashion a compute. So that makes that, especially for, you know, a lot of the AI type of algorithms, that with the same amount of compute engines that you have in your silicon, you can much more efficiently use these engines. In other words, they will be busy 90% of the time rather than 10% of the time that you would see potentially in a traditional cache-based architecture. Disadvantage of this architecture is that it's harder to program, right? And that's one of the, you know, the big research topics where a lot of people are looking into now, is how do you program these kind of architectures, and how do you kind of hide away the complexity, unleash the full potential of the architecture, but hide the, you know, the complexity of the architecture through, you know, compiler capabilities and so on. The second important aspect of a data flow architecture is that you can program, you know, the memory hierarchy and the memory bandwidth. So you can basically, in a data flow architecture, you can decide what's the width of your memory, what's the depth of your memory, and you can do that for different segments in your graph. You can allocate different ways on, you know, programming the width and the depth of your memory. So anyhow, that's some of the, you know, the characteristics, and we have in AMD the, you know, what we call the AI engine. But if you look at, you know, startups everywhere, you see this is the kind of architecture where you see a lot of startups also starting to look into. And then the third important component is that the integration between your memory and your, I mean your large memory and your compute. I think, as I said in the beginning, lot of the challenges that we see is that we are energy constrained, and when you look at where the energy is going, a lot of that is kind of wasted or consumed, I would say, by moving the data around in your system. And so we really have to, think about capabilities in how we bring, the memory closer to the computer, or the computer closer to the memory, depending on how you see it. And what you see here is, for example, how you can benefit from, for example, stacking your memory, and now I'm talking about DRAM memory, for example, directly onto your compute devices. And as you can see, there is technology that is starting to emerge now, which is called hybrid bonding, which allows you to really connect dies on top of each other with a very high density of interconnect. And so you can basically now, instead of having what you have in HBM, for example, you can get a factor of 10 in terms of picojoules per bit energy improvement for moving data around. And as we know, AI requires a lot of data movement. So gaining a factor of 10 is definitely really, really important. And then the ultimate thing is really bring the compute into the memory. That's technology that's referred to as PIM. It's processing in memory. I think in Hot Chips this year there were 2 presentations, I think one from Samsung, one from Hynix, where they are basically talking about some of the prototype devices they have and the work they have been doing. One Samsung on HBM, Hynix on GDDR, and what the benefit is that you literally in your DRAM, for every DRAM bank, in your DRAM technology, you're putting in compute engines. Think about it, multipliers, ALUs, things like that. And interesting enough, these things are running at a few hundred megahertz, right? But because of the fact that you put it right next to the data, you can create systems that are much more performant. So that's another important trend that you see, and JEDEC is starting to standardize, for example, HBM for PIM capabilities, and that's definitely something that's on the horizon in terms of catering to the requirements of AI. Now, when we talk about AI, we also have to realize that it's not all about AI in the cloud. We anticipate there's going to be a lot of deployment of AI, at the edge. And yes, of course, everybody today is talking about LLMs and recommender systems and so on. But there are literally thousands and thousands of opportunities for AI at the edge. And when you talk about architectures, depending on what kind of application you're looking at, there are other figures of merits that you have to take into account. It's not like, in the cloud everything is transactional. It's going, you want to be as fast as possible. On the edge, you want to be just fast enough, because if you're too fast, you might be okay, but you're wasting power and silicon and the like. So just fast enough is what you potentially would like for an edge device. So you have to have a capability to deal with that. And also, as I said in the beginning, what you have to start thinking of, if you think about your algorithms and how you run your applications, you will start seeing more and more people thinking about how do I combine, when I provide a solution between the fact that I have a cloud infrastructure, but I also have a client, I have laptops around there, and so a good example of that is federated learning, for example, where because of many reasons, it's either to offload the cloud on the client devices or for privacy reasons. What you do is you do some training locally on your client device, and then you send the updated parameters to the cloud. You don't send the data to the cloud. You send the parameters to the cloud, and or the weights to the cloud, and the cloud gathers, for example, from 1 million of client devices, from 1 million of laptops, gathers all that information, overnight is doing another training run based on that information, and then is downloading the upgraded application on the client devices. It helps for privacy, it helps for continuous training, and offloading the cloud, right? So that's another aspect, and that means that when you think about compute architecture, you have to think about an architecture that scales well between the cloud and the edge. Because if you have completely different architectures, different data types, different compute capabilities, different instructions, we all know that, you know, when you take the algorithm that runs on that architecture and you move it to the other, you have to start doing retraining. You know, there's inconsistency. And so what you basically would like is to have a solution that allows you to seamlessly scale your solution between cloud and edge, and not necessarily requires you know, a lot of retraining or being aware what the capabilities are of this architecture versus the architecture in the cloud and the one in your laptop and so on. So you need a consistent, scalable architecture. And that's also, like, for example, we definitely are not just preaching it, we are executing to that in AMD. If you think about it, when I was talking about the AI engine, for example, we have the AI engine as an accelerator in the cloud, and these are the big clunkers of chips that are sitting in there with hundreds of AI engines. Then you have the AI engine in the cloud, Ryzen AI was announced earlier this year, which basically gives you the same compute capability, AI engine, data flow architecture in your laptop. Very similar, it's just a smaller version of the device. So it means your compiler, you have to think about tiling and that kind of stuff. But for the rest, it behaves exactly the same. And then you have at the edge, where you really have to, once again, the same architecture, but it's further scaled down, and in a dedicated product that you can build then into your edge device. So, okay, so that's, in a nutshell, a little bit of where we are from a hardware perspective. Now, one of the challenges that we as a hardware vendor have is that, you know, the AI world is moving so tremendously quickly, right? If you think about it, I put here a kind of a, it's more a kind of a cartoonish version of the whole design cycle, that you go from requirements capture down to production silicon. But I can tell you, you know, we lived through that experience. You know, you start by kind of looking at what are the requirements before you start building your hardware, and then you go through the whole cycle. And if you look specifically, you know, in this specific case, AI, the AI world went to pretty much 3 fundamental shifts in terms of, you know, what were the important networks, the characteristics of these networks, through one cycle of hardware design. So absolutely, we need to kind of pull in the design cycle, and that, I think, will imply that we need to really do much more work on the EDA side. And so on the EDA side, I think, first of all, from a general perspective, I think EDA has been a little bit on a low burner, I think, from a research perspective. I remember when I started my career, it was one of the, you know, the top domains now, and to a certain extent it has to do with, I think, where the government is funding, and, you know, academics go, I think, where the funding comes from to a certain extent. So it's kind of a self-induced wound, I think, that happened there. But I think we have to reinvest dramatically in EDA. And there are definitely certain major things we need to take into account in the EDA world that merits that we completely rethink, you know, what we are doing in EDA. First of all, there is the whole evolution of 3D and chiplets that is requiring completely new capabilities and new tools. It requires also a much more holistic view, because you have to, combine, connectivity with thermal challenges, with mechanical challenges, and you have to look at that from an holistic point of view. And your traditional emulation of, of your system has to really evolve into an environment where you can combine all these multiple facets of designing, a chip or a system in a package or whatever you want to call it. And that's where I think like emulation will move more and more into, the concept of digital twins, where you combine different physics requirements into one design flow, and of course leveraging the cloud, right? I mean, when the IDEA world started its research activities, we were thinking about workstations, and that was the best we could get. And I think still a lot of this is rooted in, in incremental improving that approach. We have to realize now that we have compute capacity in the cloud available that is unprecedented. And in the meanwhile, also open source is going to, in my opinion, play a much more important role, because just of the size of the challenges that we face, we need to be able to leverage what other people are doing. And then, last but not least, that's catering, of course, to the choir for this audience, is the fact that we start really getting this revolution in AI, which are going to provide us a lot of opportunities. And if you think about, what AI is going to bring to the to the table here is, I know that if you look historically in EDA, in the days when I started in EDA, we didn't call it EDA, we did call it CAD. Right? Guys still seem like MLCAD, but we called it CAD. It was computer-aided design. It was like, simulators and logic simulators and SPI simulators, and get some help in verifying your designs. And then, logic synthesis and high-level synthesis came along, and people started suddenly talking about electronic design automation, right? We moved from computer-aided design to electronic design automation. So EDA became the kind of the reference. I think with the emergence of AI now, we should try to revisit and rethink about, what the next phase in this world is. And I said it, like electronic design creation. I think AI will allow us, especially generative AI, will allow us to now really, get help from turning requirements into a design, right? And so you literally are going to be able to create designs leveraging AI technology. And I think that's going to be, it's definitely something that's going to happen. And I think in the EDA world, we really have to embrace that to the full extent. But of course, that's preaching to the choir. Now, in AMD, I did a survey. Ismail, you probably know that in AMD about the engineering teams, how many of the people were starting to leverage AI in some of their software problems and so on. And we ended up with more than 100 projects where people were leveraging AI. And it goes from, predictive AI, where you're looking like debugging, supporting test, yield improvements and things like that, to at the extreme end to really start thinking about literally, generating designs from requirements. And of course, different techniques are being leveraged from the AI community there. But that's definitely the direction, I think, that we go in the design community. The places where I see most of that opportunity some of you might have seen this slide. This is actually a slide from TSMC, where TSMC says that they expect in the future the biggest gain is going to come from design technology co-optimization, or some people even call it system technology co-optimization, where you bring, you know, aspects in terms of data with respect to connectivity, with respect to device capabilities, with respect to mechanical behavior. You bring it all in one environment, and you try to really optimize over these different dimensions of the problems that you're looking at. And it will definitely also be an essential challenge to be solved, is to really shift left, right, to kind of reduce that problem that we have today, that it takes so long, you know, to go from specs to a product, and in that very fast evolving environment, you know, we are being challenged as a hardware provider there. And the way I would say I look at AI there is it's almost like AI can help. It's like an airplane, right? It gets you very quickly to the airport, and then the last mile you might need to do some, you know, some extra work there. But at least you don't have to drive with your car, you know, the hundreds and hundreds of miles. You fly, and then the last 10 miles or so you use a car to, you know, more traditionally to get where you need to be. I think that's where AI is going to help us. I'm going a little bit. Now, it definitely comes with the challenges. I started basically, you know, with a message that AI is going to solve a lot of problems in the world, but it also comes with the challenges. And as a company, that is definitely something we are concerned about. Every company is concerned about this, because there is a lot of issues that can go wrong. And especially when you talk about, you know, designing chips that end up into potentially dependable systems and things like that, you really have to be aware about some of these challenges. And some of them can be unexpected, you know, things that are happening, because, well, you know, to a certain extent, AI is very much a kind of a black box operation, and it's not like traditional software, because, you know, the way I try to tell it to people is that AI basically is software that allows you to generate software, whereas if you traditionally, you know, have software, you write a program that has an input and an output, and it does a job, and you can verify, you know, the algorithm and things like that. In AI, you don't have that capability, so that's one of the extra challenges. And then, of course, we have to be very alert for, you know, when you have rogue people there that potentially intentionally, you know, might impact what you're doing. And I'm sure you have read some in the news things that went wrong left and right, either intentionally or unintentionally. And there's a lot of aspects we have to think about in terms of IP, security, you know, use of confidential or disclosure potential of confidential information. So as a company, we definitely want to stay out of the press, you know, in terms of if people would leverage our technology in the context, we want to make sure it's secure, it's safe, it's well protected. And that's, I think today, one of the biggest hurdles, in my opinion, for the wide deployment of AI in our industry, that there is a lot of concern, because we are rooted in so many different, very important aspects of life, that there's a lot of concern that we, you know, we do not understand everything. We definitely have to have people in the loop. Explainable AI is definitely something that needs to be looked into. So that means that whenever you make a decision, when you wanted to you know, deploy AI to solve some of your problems, of course you look at the value and the impact, you look at the feasibility, the traditional engineering aspects, but there is an extra dimension now that we have to deal with, which is there's a lot of discovery going on in how to deal with all these non-technical aspects, I would say, of AI. So anyhow, in summary, I would like to say that clearly we are on a path towards creating solutions that, as I said, we just installed the first exascale compute infrastructures. I think 5 or 10 years from now we will be at zetascale level. All of that will be driven by AI. But energy, more than anything else, is going to limit what we can do, and we have to really take that into account. And there are, definitely knobs we can turn, new architectures, new technologies, and we basically have to leave no stone unturned, I think, in order to get there. And I think, yeah, AI is opening up, in my opinion, a new era in design automation or design creation, no matter how you will call it. And we have to fully embrace that in order to kind of cater to the requirements that are coming towards us from a hardware perspective. Right, thank you.
One very simple question. So probably AMD is one of the few companies, maybe only one company can provide all the very strong performance for CPU, GPU, and FPGA now. So, but I haven't seen a real product that really combine all of them into a same chip. So do you have any comment or idea whether that's in the future roadmap?
Yeah, I could tell you what's in the roadmap, but then I have to kill you afterwards, I guess.
All of us.
Yeah, that's right. But, well, I think we are going in a direction, right? I mean, I mentioned the Ryzen AI technology, which is basically x86 combined with an AI engine accelerator, all in one device. And I think it's a first step, I would say, in that direction. If you look at the MI300, MI300A is basically a device that has 3 CPU chiplets in there, and that has 6 GPU chiplets in there. So you start seeing this coming to fruition, right? And yeah, so I think you have to realize we are a little bit more than a year now. We merged the two companies, and I think I'm very proud that already in the beginning of the year, which is 1 year after the merger, we already announced a product where we combined the AI engine, which is kind of has this legacy into the FPGA world, right? If you blow your eyes at the AI engine, it's kind of like an FPGA. Think about replace lookup table by a VLIW superscalar, and for the rest you have the concepts are very similar, right? So there is a lot of FPGA knowledge that has gone into that domain. So it's not going to be black and white that you will see, okay, this is an FPGA and this is a CPU and so, but there is definitely a lot of cross-fertilization between all these different technologies now.
So Ivo, I have a question. Excellent talk. You bring together all the aspects of design, architecture, application, and in my head, it's almost a replay of what we saw in the USB world for, I would say, between 1980 and probably 2000. And one of the lessons we learned there was that in the end, what wins is not the architecture but the compiler.
Yeah.
And you did talk about that as being a bottleneck. So I want to come back to 2 comments here. One, you said that the existing architecture is, sometimes is only 10% utilization of the compute, right? Because the architecture, and some of it is also in the compiler, and the architecture you talked about, it gets rid of some of the architectural inefficiency, but then it shifts the problem to the compiler. So if you look at the crystal ball of AI, and I frankly think this is where the whole AI world is today. There are people with great chips and great architectures that are going nowhere because they don't have compilers. And then there's stuff from The big players, we want to name them, who are excellent software environment.
Yeah.
Doesn't matter what the architecture is, they're on the market. Right? So how do you think this is going to play out and evolve? And where do you see key technologies coming from? Because in that world back then, DSP, there were some breakthroughs. Really good compilers for like the TI DSP, and that changed things.
Yeah.
So from your view of universities, what is going on in industry, where do you think this is going to converge?
Yeah. Well, that's actually one of my soapboxes, because I really believe that as a research community we have to come together on the work on compilers. And one of the things that we in AMD definitely embrace a lot is the initiative, the MLIR initiative, which is basically an open source effort where you kind of provide intermediate representations of kind of higher level architectural concepts, and then you allow compiler steps that map onto these architectural intermediate representations. And there's a lot that you can leverage for different architectures. So my view is that you will have the MLR community that will introduce all these intermediate representation of architectures, which are kind of reflecting certain characteristics of architectures. And you will have the community that will build compiler steps for that. And then it's right at the bottom, you will have the proprietary last step, that maps into the real hardware. So that's I think, how I think we will be able to deal with, the challenges of the compiler by a lot of open source capabilities. And for the time being, I think the MLIR initiative, I really believe is something, at least in AMD, that we embrace.
Any other questions or comments? Okay, thank you very much, Ivan.